So last week what we were looking at was all the oh god, do you guys have any? Give me a pen. Yeah, normal pen. Yeah, okay. Thank you. So last week what we looked at was the first electroweak precision parameter, which we call it as delta rho, right? Okay, so this essentially uh, this last time we used another definition. Oh, okay, I didn't bring my other notes actually. So what would we? There are many definitions. So we use the definition delta rho is equal to pi ww by nw square minus pi zz by mz square. Is it right? That's what I think we used essentially. So okay, we can use various now instead of pi ww and pi zz, you can actually use it as delta rho as a splitting of the first two isospins up and down 1, 2 and 3 also. So you can also write it as source so the starting of electroweak precision test, actually if we want the rho parameter, is can be attributed to Weinberg. He wanted to preserve the relation between mw square cos square theta w. So he wanted to preserve this relation, and that's the reason why he introduced the tree level rho parameter, which we define it when rho is equal to 1, this relation is always holds. And if we have radiative corrections, we should have small corrections on both sides, and that's how you define delta rho. So along the way, we also introduced how to calculate the self energies and also the vacuum polarization graphs of the W's last week essentially. So sigmas and pi's. So the sigmas contain also the bosonic contributions, and the pi's will. So when you renormalize, you classify it in such a way that certain class of diagrams go as vertices, certain classes go as renormalization of the couplings, certain classes go as for self energies, essentially the mass corrections. So the reason is obviously when you do the actual calculation, when you actually do the thing, you can actually check what it modifies. If it modifies the mass part of which comes in the numerator, or what does it modify essentially. Okay, when you actually do the calculation. Any questions? So the first electroweak precision parameter we checked was rho and delta rho, and then we saw that in BSM models, okay, this is measured in BSM this is a measurement which is accurate up to 4 decimals, and in BSM models, even with a single extra Higgs, this gets modified essentially, or anything which violates the custodial symmetry will get modified. Again, what is the custodial symmetry? It again goes back to Weinberg, essentially that the custodial symmetry protects this relation, and this is coming from the Higgs essentially. There is only single Higgs which gives masses to both W and Z, and this can be traced back to the currents, how the broken generators of the Higgs, of the SU2 components of the Higgs are related with each other, okay, because the broken generators of the SU2 component. Then there are a lot of calculations. So then we derived this delta rho to be dominated by the heaviest particle, which is essentially the top quark. So this is the physics. In addition to all the formula and everything, this is the physics we should remember. Now, if we have an extra new generation, and the generation should be necessarily heavy compared to the standard model particles of the 3 generations, and in that case, the delta rho will be dominated by the heaviest particle, okay, of that particle, and this gets violated essentially. Okay, this gets violated. Anything which modifies your custodial symmetry, super partners, what happens is for every stop, every top there is a stop. Okay, so the contribution will not just go as top square and everything, but it goes as top square sum q square by mz square. So let's say mz square. Okay, so this is can be very small. This can be of the same order as, okay, and this stop, as it increases, essentially it won't be quadratic in the supersymmetric case. Everything will go as a log. Okay, even if the stop is 1 TeV, so you can forget about the top contribution, it will still go as a, so this is called the decoupling limit essentially. So every top contribution is cancelled by the equal and opposite similar mass by super partner. So that is the only theory which is, as far as field theory is concerned, it is very extremely well behaved. Supersymmetry, that's the reason why people like it so much. It is actually a fantastic theory. It protects the Higgs mass, and you can do all the calculations systematically, and it is extremely well behaved. It doesn't violate any of the electroweak precision tests. So we'll also look at one coupling today. Another, before going further, okay, now delta rho is measured in terms of only at Lep. Even before delta rho was measured at Lep, there was even older result in the 50 not 50s, meaning one of the first results in the Fermi theory, even before the standard model was formed, radiative corrections. Okay, radiative corrections in the Fermi theory, and that though we looked at delta rho first, but the first actual thing which was proposed is called delta R. This comes in the radiative corrections to the muon lifetime. Okay, muon lifetime, this is also important right now. This is, it can be measured more precisely compared to say neutron lifetime. Say, what is the neutron lifetime? How many? 15 minutes. So, but muon lifetime, how much? Yeah, 2.2 microseconds. Are you sure? Anybody else? Is it microseconds, milliseconds? Okay. So the muon lifetime was first calculated by again Sedlin in the 50s essentially. Okay. So the first radiative corrections were done in Fermi theory. Okay. But then now this has to be modified for standard model. Okay. So GF by root 2 is equal to alpha pi 8 6 theta w and w square. Now the muon lifetime in Fermi theory, though it was done, was just a point interaction where you have mu going into nu mu nu e electron. That was the decay. Okay. In the standard model, this becomes complicated. Right? Do you agree with this? Okay, there's nothing. I just expanded this blob, this gets explained. So even though the first radiative corrections of the standard model were done in the 50s, it was not in the standard model in real sense because it was just Fermi theory essentially. Okay, there was no standard model at that time. So at one loop, so what do you mean by muon lifetime? Muon lifetime, how do you calculate it? Meaning decay width, how many of you know? It goes as 5th power of muon mass essentially. Okay, you read your Giffords. I think the first calculation you do is calculating the muon lifetime essentially, and it goes as the 5th power of muon mass plus some constants, 192 pi. This number you should all remember, this formula. Okay. Okay, this is the first thing you do essentially in your calculations. So this goes as 5th power and it goes as GF square. Okay, so if you make any corrections, if you want to measure precisely this, so that means what you are renormalizing is only GF square. Okay. Nothing else. Okay, the muon mass will be very limited correction. What you are doing is the correction to the GF essentially. From there you can get information about GF. So the GF correction is what it was first started there, though we looked at delta rho. So the first ever calculation was done by on GF essentially. So at one loop, this relation gets modified So you have corrections at one loop from box diagrams. Okay, box diagrams will be something like this. Okay, we'll do. So vertex diagrams. So you have vertex means plot them here. So there will be a vertex calculation contribution. You can also put this thing here also. Okay, vertex, and you can also have a box. So the one loop would be GF cube, right? It will be GF cube. Okay, so you have 1, 2, 3. What I'm saying, GF square. Sorry. So you have box contributions also. So what you do is after renormalization, this entire thing, I am not writing the explicit expressions, you can find it in the notes. So again we do the same thing like what we did earlier. We just say essentially E0 square equal to E0 plus delta E, and MW0 square equal to MW. Uh, uh, no, MW square. MW is equal to delta MW. Same thing. We do all that, put it back into this relation, and we end up having something called, in terms of the renormalized quantities, okay. So GF renormalized is equal to the variation in GF is called delta R. Just like delta rho is a variation in the mass ratio, okay, the variation in GF, which includes this plus this plus this. So it includes vertex plus box plus self-analysis. Okay. So this entire contribution is called delta R. Now this part we already calculated. Okay, we know what it is essentially. SW square. This is S0, M0. No, this is renormalized quantities. And we know, we saw this last time, we saw this, we saw delta SW also, it is a same thing essentially. Okay, putting all these things into consideration, we can calculate what is delta R. The only thing which is missing is vertex and box. Vertex and box you can find in the notes essentially. The result for the vertex and box. And then, so the delta R is written in terms of delta rho as well as alpha, delta alpha essentially. So after putting everything, so the calculation of box and are given in terms of these logarithms, which is alpha by pi sine square theta w, delta minus log mw square mu square, and so on. So finally what we have, delta R essentially is given again in terms of quantities which you can compute. Now this is our definition of delta rho. Okay. Okay. Yeah. I'll only this is a long expression. Should I'm just wondering. So anyway, okay. I hope I have written it correct, but we can check it actually. I can check it. Essentially, it's there in my paper also. This multiplies this. Now, what we need for this is pi gamma gamma 0. Now, pi gamma gamma, is it measured precisely? Okay, pi gamma gamma. So it depends on pi gamma gamma, delta rho, and all these other pieces essentially. So various pieces. Okay, gamma z we calculated it essentially. Gamma z we calculated it. It goes to 0 at I should go to 0 at q square is equal to 0 we have shown essentially. Okay, pi gamma z and everything, sigma z. So after all that, essentially this all can be absorbed into delta alpha. Okay, So the largest error comes from this particular thing. In all these measurements, the largest error comes from this pi gamma, pi gamma. Okay. So in all this electroweak precision test, what you will see is some parameter called delta alpha pi hadronic. So what is this? So this is the same thing which also affects your G minus 2 also, essentially very similar thing, but also affects your. So pi gamma gamma, it interacts with there are quarks, leptons. Okay, this is also called hadronic vacuum polarization, HPV, in G minus 2 essentially. So what happens if you have gamma gamma? You want to see the contribution of this to the variation in alpha. Now here you have leptons and quarks. Now how do you calculate? You can calculate the quark contribution, but the masses are not very well known. Okay, so you don't really actually calculate it. And if you are working at LEP energies, you only put in up to bottom quark. So only 5 quarks are there. You don't care about the top quark mass essentially. The top quark would be virtual essentially. What is it? Now light quark masses are unreliable. So bottom quark you can measure it. So you can measure it in an experiment and everything. What is the contribution? Bottom quark you can do it. But if you have light quarks, there is a large variation in their masses. Okay, so for example, you don't know whether to use up and down. Say for example, if you are using up and down quarks, you don't know their masses. Their masses have roughly 2 to 3, 1 or 2 orders of magnitude. Whether it's 5 MeV or 30 MeV, what is the thing we should use? So factor 6, factor 7 difference essentially. So you cannot really calculate what it is. So what you do is using the optical theorem, and you cut it off, and then use something called a dispersion relation. So E plus E minus go into light quarks essentially. Light quark means pions. So use the pion data, E plus E minus to light pions, and then try to estimate what is this. Okay, so this hadronic pi gamma gamma part of it at mz square will be some alpha by 3 pi mz square by a kernel starting with 4 m pi square to infinity ds prime r gamma s prime. So the light quarks, you have to use this kind of dispersion relation where the kernel is what is given by this particular. This is well known. Now you have to use this data, but this data itself has a lot of errors. Okay, how well you measure it will also propagate into this entire contribution is absorbed into this quantity called delta alpha phi hadronic. Now just to show you the difference between how well this is measured in experiment compared to the leptonic case. Okay, the estimates in terms of the leptonic and everything. I'll write down the numbers. Then I'll show you some graphs essentially, some figures. So the delta alpha E mu tau leptonic is equal to 0.03150 plus minus essentially for all practical purposes 0. Okay, negligible uncertainty. Delta alpha top quark 0.0007 small contribution because this is mz square, sorry. The top quark contribution would be very small because it's heavy compared to at mz square. So you can neglect it, like that's the reason. So what is left is quarks, light quarks essentially. So this one this is the largest uncertainty. So these are essentially 0 point. So the leptonic will be the dominant one, a comparable one in this, but this has 0 uncertainty, but this has uncertainty in the 4 decimal. So this contribution, pardon. Pardon? Why the top is negative? That I think is I'm not sure essentially. Oh no, because it's massive than mz square. Yeah, it flips. The log sign flips. At mz square only, essentially, in general. So this propagates everywhere. The neutrino direct search, non-standard interactions, of course, but we don't do renormalization there essentially. Okay, okay. In most BSM models, we don't do renormalization as long as they are decoupling. If they are in principle, you should do. If there, that's say for example self interactions, dark matter self interactions. Okay, they are pretty large, so they will have effects everywhere actually, because can you build, if you want to call it as a particle with such large self interaction, it would violate all kinds of theoretical constraints, okay, in quantum field theory, okay, unless it's strongly coupled. So it can violate unitarity, it can violate all kinds of stuff essentially, like what we saw for the Higgs, meaning without the Higgs it will violate the unitarity. Such large couplings are extremely hard to deal with. Similarly, if you have any new interaction, even with neutrino or something, if it is light, it will modify GF correction and it will has to be put in there essentially. And the GF, as you see, is delta R is very strongly measured except for this uncertainty. Okay, so how do you measure this? This delta R, essentially R of R gamma. This R of S is essentially sitting in that, is sigma E plus E minus going to gamma star going to hadrons, sigma E plus E minus going to gamma star. Okay. This is the same R which you have used, right, in your particle physics course essentially, where leptons versus hadrons, where you have U plus E minus going to Z prime, Z star going into U plus E minus, just to get the color factor essentially, the factor 3 and everything. This is the same. Finally, after all doing this, okay, and calculating everything, and you can write down delta R in a simple fashion as delta R is equal to real of pi gamma gamma at mz square minus alpha by 3 pi cw square minus sw square by 4w sw square log. Because the gamma z contribution goes away at non-zero zero values of momenta and everything, doing all that stuff essentially. So delta R can finally be written, okay, after all that, okay, there is, after several intermediate steps and everything, I showed you there are pieces coming from delta rho and everything. So with this, you can add delta R is equal to delta alpha minus cw square by sw square delta rho plus delta R remainder. I'll tell you what these are. This is the formula. If you remember, you can calculate things. Delta alpha will contain the error coming from delta alpha leptonic, delta alpha top, delta alpha hadronic. Fine. This will contain the error. Okay, the largest error in all these three. Delta rho we know, we have calculated it. Delta R remainder will contain delta R top, delta R Higgs. So this is not added in the bosonic contributions of the delta rho. Not delta rho is essentially you keep it only for the not to the correction of delta, to the correction of GF, the Higgs contribution. When you write here delta rho, you are really worried about uh, the mass renormalization essentially, and the vertex correction and other stuff of the Higgs is put here essentially in the remainder. Okay. So it's very nice that they can organize this entire complicated renormalization in terms of this, in terms of mass renormalization, and that is essentially delta R, which is coming from Higgs and top, and coupling constant renormalization of delta alpha. Why should delta alpha come in? Because in the variation of GF, because there will be corrections also from the photon essentially. Okay, because we saw that it's very small, right, at mz square essentially. So within the standard model, there are also higher order corrections, two loop corrections, and for this some two loop corrections have been done for delta rho. Okay, like I said, full two loop calculation of the standard model is not completely done. Renormalization, as you see, one loop itself is super complicated, but we could get most of the information further. Then there are QCD corrections and everything. So for all practical purposes, delta R is not very sensitive to the Higgs mass. It's not very sensitive to the Higgs mass. Okay, it's not extremely sensitive, because as you see, it goes as a log of. But if there is something which is very sensitive, it would be meaning the electroweak precision tests are not very sensitive to the Higgs mass in real sense. So even if you measure them very well, okay. So then there is, somebody was asking about neutrino scattering, right? Essentially, so again, neutrino scattering is sensitive to sin square theta W, charge current over neutral current essentially. Okay, and from there you can get very precisely sin square theta W. Okay, which is important to in this measurement. Delta rho you know, delta alpha you know, and reminder, these are not very sensitive pieces, they are very small. So if you know delta rho and delta alpha very well and sin square theta W very well, so you can measure delta R pretty well. Okay. Now sin square theta W, the main thing comes from the measurement is coming from neutrino scattering, charge current versus neutral current essentially. So you can see R nu is equal to sigma nu neutral current by sigma nu charge current. So this goes as essentially mw square or 4 mz square. It is sensitive to the fourth power of this ratio, so the sin square theta W4, so it's super sensitive to sin square theta W essentially. So 1 minus 2 sin power square plus 10 by Similarly, you have an expression for anti-neutrino scattering. Okay, very similar expression. So sigma nu bar NC by sigma nu bar CC. This is also the same ratio. In the same expression, except wherever there is R, you have to replace it by 1 by R. And R is this, small r is this ratio sigma nu CC by sigma nu CC bar, which is around 0.4. Charge current ratio of neutrino scattering versus anti-neutrino scattering, okay, is around 0.4. Should remember the neutrino and anti-neutrino scattering are not the same. They have difference about half essentially in the charge current. So these experiments give you sin square theta W. Where is the nu tau is equal to point sin square theta W 0.22. Oh no 2277 plus minus 0.0016. And then there is something called very old experiment, CCFR, charm, CDHS. These are extremely old neutrino scattering experiments. Those data we still use it, especially for sterile neutrinos and all those scattering effects. So these all give you a number 2253 plus minus 0.0047, and this is called, this difference is very large within the neutrino scattering experiments essentially. So this is called, and it also doesn't match with the global sin square theta W fit. So this was called the Newton anomaly. So this is called the Newton anomaly, and in electroweak precision test, whether to take, when you do a global analysis, okay, whether to take Newton into picture or not is a big question, because it will spoil your full global fits. So okay, so this is 3 sigma away. And also from SM predictions. So now sin square theta W should be measured very precisely so that you can estimate delta R very precisely. Okay. Now you can take sin square theta W from left and just SM measurements, but Newton measures it much higher because around 3 sigma level. So that will, if you take Newton, that will propagate into delta R and everything. So all the things are extremely tied up. So when you are doing global electroweak precision test, you have to be extremely careful because you have to choose what are my input parameters and then predict rest of the parameters. Okay, you have to choose what are your input parameters. Suppose if I choose gamma sigma z, okay, mz, okay, if I take 5 of them, essentially I predict rest of them and then check with the experiments the rest of the parameters, essentially rest of the parameters. So okay, so all the parameters are interconnected. Suppose if I choose delta R as my input, okay, then you can predict sin square theta W and everything else. So you have to choose 5, which of them are 5 independent parameters. Typically you choose the ones which are very well measured, essentially, when you are doing a global analysis. We'll come to that in a second, essentially. Okay, I will come to that. Why? You don't know yet that you deliver the random. Right. The scattering is different because one, okay, yeah, neutrinos, they participate, they interact with what? Neutrino. So the antineutrino interacts with antiparticles. So if the target essentially doesn't have enough antineutrinos, essentially, right? Yeah, antiparticles, essentially. Yeah. So it only can interact with Z. The W scattering is not there, essentially. So particle, if it is a particle, it will interact with W, right? Essentially, right? With antineutrino, the coupling changes. Okay, you can find it in the notes, essentially. Okay. Yeah. So finally, I will just write down delta R value so that we'll just see 0.03648 minus plus, sorry, 0.00028 plus minus 0.00013. Okay, this only happens in your name. I forgot your name. Excuse me, your name. Huh? Aryaman. Okay. Now, if a theory is not parity violating, say if it is a vector like QED or something, the left meaning then there is no distinction between left and right. Okay. Suppose in it now, so the particle and antiparticle cross sections, if you look at in say QED, they are very minimal. The difference between particle antiparticle quotients. Okay, and if it's not C violating and everything, if it's parity violating, the left-handed neutrinos and the right-handed neutrinos are coming in the same thing essentially. Okay, so the representation nu well contains left-handed particle, right-handed antiparticles. So the antiparticles are always right-handed essentially. Okay. Okay, so we came to two parameters which are essentially a delta rho and delta r. Now we can look at other measurements. So delta r you can look at so the two parameters in but what we want to measure are explicitly what can be seen in an experiment. Okay, so these are something which we are deriving for our case essentially because we want to put it as coupling. This is as mass renormalization and everything, but this is for what are measured at LEP, what are explicitly measured at LEP essentially. So what are explicitly measured at LEP are so they also contribute to the precision measurements. They are the ones which contribute. So say for example, what is the LEP do the physics with? So when you are talking about these are your fits essentially, you put it back into your calculation essentially, but you want to write down everything in terms of what are measured essentially, what are measured. So the only thing which we know what is measured essentially is the delta alpha sin square theta w, which is measured in terms of this neutron scattering. Okay, and LEP it is measured due to something called forward backward asymmetry. Okay, it is measured to we saw that sin square theta w is measured by neutrino scattering at the elsewhere. At LEP it is measured by forward backward asymmetry. In addition, LEPs also measures there are other measurements which are done at slack. There is something called SLD and everything. Okay, so all these measurements are put together and done a global electroweak fit essentially. So they are done into something called a global electroweak fit, which goes either something called Z fitter, which does it. But earlier there was something called the LEP electroweak working group, which actually did all these calculations, put together all the data, and predicted what it is. So what happens in LEP? LEP essentially is a thing. All this business started with LEP, essentially E FF bar. Okay, so this sigma contains gamma and z, contains gamma and z. So what we are interested is this one, right? Essentially there is an interference term other than the QED contribution, and if you want to measure the standard model, we have to worry about this z contribution, essentially the brutal term. So this sigma is given by 4 pi alpha square by 3s 1 plus a1, where a1 is equal to 2 vl square fz plus vl square plus al square whole square fz square, where fz is equal to s minus mz square 1 minus sine square 2 theta double. So what we did here, essentially factorize the alpha part. This cross section contains two contributions, one is with photon, one is with z. Added both of them, took the square of it, and wrote the entire thing in terms of alpha square plus some factor which only contains the z part. So al is equal, a1 is equal to 0 means QED contribution, a1 not equal to 0 means the z contribution, okay, including the z contribution. So a1 is equal to vl, vl is the vectorial contribution coupling, al is the actual vector coupling, and fz is this contribution s by s minus mz square 1 minus sine square theta w. So we can play around this, but at z pole so s is equal to mz square. This entire thing s by s minus mz square goes to you can put a square on this, becomes s square s minus mz minus I by 2 sigma z square whole square. So the width of the z comes into the picture in the propagator. This is standard prescription in all quantum field theory is essentially for unstable particles. Essentially for unstable particles, what we do is essentially in the propagator you modify the mass with the corresponding width of the particle, essentially. Then depending on whether the width is here we are narrow or meaning broad width or something. Broad width means essentially it's it has a lot of decay modes and everything. Essentially narrow width means it has, so we just take either narrow width approximation or broad width. Now remember that broad width means it has a very little lifetime, okay, and narrow width means it has reasonable everything is because okay what do you mean okay, right. So you do this and you can define at those case sigma e plus c minus go into ff bar z pole at the pole of the propagator, essentially. That means when s goes to actually mz square minus I gamma z and everything, okay, this is called the z pole. The formula becomes roughly approximately equivalent to 4 pi alpha square by 3 mz square 1 plus dl square al square vf square plus af square. Here L is essentially E sine power 4 2 theta w into mz square by gamma z. You see, the formula is simple. With this, you know all left physics. Now imagine that in addition to here, you can put everything, anything which decays into ff bar. Suppose if you want to if you want to modify with anything which z prime, kinetic mixing with some z prime, essentially you have to modify with coupling constant accordingly here, and then kinetic mixing term will be there, that will modify this coupling constant, will come with some angle, and you have to put whatever the dark matter mass particle or something mass here essentially. So this will contribute to the invisible decay with the. Okay, so every particle will have its own width of z. So z decaying into ff bar, the width, partial width of that particular particle. So this will be alpha mz vf square plus af square by 3 sine square 2 theta w. So this entire thing comes out to this fantastic master formula. So the max, we call it as max essentially, is equal to 12 pi mz square gamma e gamma f gamma z square. See, the width of the electron we know essentially z. Any new particle, so every partial width can be measured essentially. Z going to BB bar, Z going to invisible, Z going to everything can be measured very clearly at one look. In the experiment, very precisely. Forget about, we are not doing theory here essentially, we are not doing one loop calculations to E plus E minus. Okay, these are tree level, but tree level matching is sufficient essentially to get the partial widths, and these partial widths you can calculate in theory at higher precision. Okay. So with this, I am spending a lot of time on ultraweak precision test, but I wanted to show you some more graphs, but anyway, but I'll do that. So you measure E plus C minus going to E plus minus at Z pole, that gives you gamma E. What is this called? This is called Baba scattering, no? Essentially you measure that essentially Baba scattering at Z pole, and then you can measure it for say mu plus mu minus, tau plus tau minus, BB bar, and everything. Now neutrinos E plus E minus going to nu bar. Does it have a gamma contribution? It won't have a gamma contribution. Okay, it won't have a gamma contribution. So this is called gamma invisible is equal to gamma z minus gamma gamma visible. So that is gamma z minus gamma e, gamma mu, gamma tau, gamma hadronic. Gamma hadronic means everything, BV bar, QQ bar, everything. So you can measure the total gamma hadronic, mu E tau, remove it, and that's how you get your Z invisible. So this graph I showed you last time, essentially this measurement. I think lecture 4 or something I showed you. So this is one measurement, various gammas. Okay, mz is well measured, gamma z. So if you calculate gamma mz, gamma z, and partial widths, you can get gamma visible. But for electroweak precision test, what are the other ones? See, physics contain lot of stuff, but we will be concentrating only on the electroweak precision test. Okay, so each one gave constraints on BSM physics, but okay, let's for the present, the invisible decay width puts constraints on many things. Okay, just like invisible decay width of the Higgs will put constraints on lot of stuff, which hopefully we'll do at a later stage. Essentially, when I do the Higgs physics, I'll do that invisible decay width of the Higgs also. That also can be done systematically, like a very similar way. For example, if you have dark matter coupled to the Higgs, okay, that also will have constraint from the Higgs invisible decay width of the Higgs. This you have seen, Devjati. Okay, right. So then, what are the other measurements which are important? Now, if you write the differential cross section, E plus E minus going into L plus L minus. So d sigma by d omega. So you are not writing the total cross section, but you are writing the differential cross section of E plus E minus going into gamma z L plus L minus. This again can be written in very similar form, 64 pi square s 1 plus a1 I introduced earlier, plus 1 plus cos square theta plus a2 cos theta. And a2 is equal to 8 bl square al square fz square, the same fz, plus 4 al square fz. I'll put all these references in the Teams page, and also all the files which we use will be okay. It's a collection of many things actually. So okay. Now you see A1, the Z contribution A1 has the same thing as QD, 1 plus cos square theta W. So okay, A1 itself is, what makes the difference is A2. A2 is again purely given by Z. The differential cross section of A2 is the one which makes a difference. Okay, A1 has the same contribution, so as QD it won't make it tell you whether it's the theory is parity violating or not, so forward or backward. Okay, only the A2 contribution will make a difference. So what you do, So it makes life easier. I should get some chalks here essentially. Forward backward asymmetry, leptonic, is defined as maybe I'll write it again. Leptonic 0 Okay, you understand? It's just same terms with a plus sign. Okay. I can write it down 0 to pi by 2 d theta sine theta and when you compute it, this comes out as 3 by 8 a2 So if A2 is equal to 0, there is no forward backward asymmetry. So if there is no Z boson, and if Z boson is not parity violating, there is no parity value. Now you can actually say one of the important thing is now you can measure it for gamma B, sigma B. It's random model. So if you have forward backward asymmetry for the bottom quark, E plus E minus going to bottom quarks, and it turns out this is given by GF by mz cube 3 pi root 2. Now if we look at the couplings, T3b minus qb sine square theta w whole square plus minus qb sine square theta w whole square now if T3 is 0 of the bottom quark, this measurement will tell you that some number will give you essentially. Now what happens is if you put T3 is equal to 0, the measurement came out to be something like 376 MeV. T3 is T1, T2, 3, no? T3 is the I3. T3 is T1 plus T2, the isospin generators, right? Right. T1 plus T2 and T3. The Z couplings are given by in terms of T3 minus Q sine square theta W, right? Okay, this is the T3 value. If bottom quark is okay, TB, right? So the upper part would have positive half and the lower part will have negative half, T3 values. So that is the T3 value, right? Okay. Okay, I'm sorry, I was a bit stumped when you asked me what is T3. Okay, right. We are going beyond the standard model, but okay, all right, okay, yeah, okay. Now, suppose if there is no top quark, so if you are doing the lab physics at 90 in year 1992, top quark was not discovered. T3 is equal to 0 will give me some number which is like 23.5 MeV. If I put T3 is equal to minus half, this will give me 376 MeV. This is close to the measured experiment. So it indirectly inferred that there is a top quark already without actually discovering it. So our thing that bottom quark comes as an SU2 doublet came out to be very close essentially. Okay. Now this is about forward backward asymmetries. Then there are other asymmetries. What I am doing with time? Okay. I'll also introduce this one before showing you. I can take 10 more minutes, right? Essentially, I'm a bit late essentially. So there was this experiment at SLAC which was called SLD. SLAC SLD, which has measured something very similar like forward backward, but it's called Lepton asymmetries because it uses polarized targets. Polarized differential cross section at Z pole AF again is in terms of couplings 2 VF AF by VF square. These are just the couplings. So this was measured at SLD detector at SLAC. So this you can now they had polarized targets essentially. So PE is the amount of polarization essentially. Okay. Huh? Polarization percentage of the polarization. ARs are the couplings. AE is just the E, replace it with E. So they had very similar forward backward like asymmetries, which are called A left right, these are called lepton asymmetries. Now these are independent measurements compared to lep. Okay, the SLD measurements are independent measurements. When you are doing global electroweak fit, you have to consider them separately. Okay. Now this also gave you a sin square theta w and ALF left right also. Okay, these measurements I'll show you in a graph essentially. So sin square theta w effective 0.023101 plus minus 28. It has a measurements independently compared to left. So the entire data also had AE. These are the AEs, asymmetries. So then I'll come to lepton universalities essentially. Okay. Okay. Lepton universality measurements also were done. So ALR left right is measured by 1.1108. Sorry. 00218. At Z pole with electrons essentially. This with Z pole with electrons. Now they then did the same analysis, but now they also defined electron asymmetries essentially. Okay, forward backward asymmetries. It's called lepton asymmetries. This is left right asymmetry. Okay, then there is something called electron asymmetries, lepton asymmetries. The physics there is E plus E minus the coupling of the electron muon tau is the same for the Z. Okay, the coupling of the electron muon and tau is the same. So except for the kinematic factors, if you measure the decay widths of the Z to electrons or muons or taus, except for kinematic factors, it should be roughly the same. Now if you take asymmetries, which I will define in a second, so the kinematic factors also will go 0. So this is a measurement of lepton universality, which is a fundamental prediction of the standard model. So lepton universality essentially tells you that apart from the kinematic factors, the couplings of the Z to the 3 leptons are the same. So yeah, you're saying something. Yeah. So it is over constrained. So there are measurements from mu tau, there are measurements from SLD, there is a measurement from LEP. So there are a lot of measurements. Yes. So when you are doing a global fit, you have to take all the systematic uncertainties for each of this and the statistical uncertainties and do a correlation matrix and do a full analysis. So angular distribution, each lepton asymmetry at Z pole, these are only done at SLD. So this will be PE plus 1 plus cos square theta W plus 2 mu or tau. Replace it with essentially this one AE minus PE cos theta. The same asymmetry is measured for electrons, muons and taus separately. So after several years of data, the measurement is 0.1158. This same thing which I wrote earlier, essentially plus minus 0.0064 A mu 0.137 plus minus 0.016 A tau is equal to 0.142 plus minus 0.016, and this is consistent with Lepton universality, which predicts A mu up to the kinematic factors 0.523 plus minus 00. Muon tau, there is only kinematic factor difference, the couplings are the same essentially. Okay, so this should go to 1.25 if you take care of the kinematic factors. So Lepton universality is a very strong constraint coming from Lepton asymmetries from SLD. So we have seen almost all measurements which come at LEP. So we can try to see some plots, maybe. Yeah. Okay. So most of the theory is done. We have done the renormalization, except for the STU parameters essentially. Okay. Okay. Then I'll do the STU parameters also, and we have seen the collider physics measurements. Okay, how to match with the measurements. Before going to data, I will define what is STU parameters and then show the figures, the data. Okay, and maybe I'll stop here today. Essentially, it's already 1:10. So, any questions? So instead of 2 lectures, I am taking 4 lectures. I think on electroweak precision test, but this is important actually. I think this is fantastic measurements which will have implications if you have any new particle beyond standard model, any particle which is charged under any particles. This will also have implications for milli charge, all kinds of things.